So let us start with a brief review of the last class. Understand if you have any doubts in the last class, and then we will move on to the subsequent discussions. So good morning, and if you have any questions or doubts in the last class, I would suggest you to ask first. So any of you have any clarifications or doubts required from the last class? No doubts are there? Okay, then I am sharing the screen. Okay, let's go back to the discussion that we had. I will just very briefly review. What is that we were discussing in the last class? Can one of you tell quickly? 1 or 2 points on that. What is that we were discussing in the last class? What was the content of the last class? Yeah, Prakash. Yes. Bhavana and Sneha.
We talked about neuron learning of parameters, cost function, and further vectorization of the loss function.
Okay, so we discussed about first a neuron, and then the cost functions, different cost functions for training the neurons, and then the learning rule. So essentially 5 elements of machine learning. So that are very important for any classification problem or for many other machine learning tasks. So in fact, for task to task, there may be some difference. So that will be the 6th element you can consider. What is the task we are doing? But in each of the tasks, you will have all these 5 elements. Okay, that is starting from the data, input-output pairs, if it is supervised classification. Okay, and then you will come up with the weights, which are to be learnable parameters. And then there is a cost function through which you will learn. And then there is a learning algorithm, which is helpful for learning and so on. Right? So, and then we discussed more about the neural network, feed-forward neural network. And training of feed-forward neural network. We have seen in the previous classes how to do it in a scalar form, when especially using chain rules. So in that we have seen that actually the weight update, each of the weight update happens independently of that weight. So so if Wj is the weight to be updated in a particular layer, then what we do is Wj is updated using gradient descent rule. Okay, so that we know. And this is what kind of classifier is this? So when we consider only one layer, what kind of classifier can you tie this to? So do you think that will it be able to do nonlinear classification if there is only one layer, or is it a linear classifier yet? Any answer? Bhavana?
If there is only one layer, we can use it for linearly separable data.
Right. So it is still not a nonlinear classifier because there is no nonlinearity involved, okay, in getting the outputs. So even each output may have a nonlinearity in terms of the activation function that you use here. But still there is the output function, if you see, there is a still each is a linear output. Okay, so that means just giving a nonlinearity doesn't mean that they can separate the class samples, class 1, class 2, class 3 in a nonlinear space. Okay, so it's still giving just a transformation to each of the outputs you are getting here through whatever the f you have. But the nonlinearity across different features is not taken care. Okay, so you need at least 2 layers to bring in classification for non-separable samples or to get a non-linear decision boundary. Okay, this still is a linear classifier. Okay, so except that instead of taking the direct scores that are there after like net values, you are taking the scores with a modulation f or with some non-linear function f. Okay, that's only either a changing the dynamic range essentially. Okay, is this fine, or mapping a couple of things to one and other couple of things to other class and so on. Okay, so then we discussed about a differentiation in a scalar form, which is similar to what we have done. And then we started looking at the vector differentiation, considering that, say, considering to see actually what is the advantage of vector differentiation over scalar differentiation, and also to acquaint ourselves with vector differentiation. So in this class, what I will do is, I will give some of the, see, we started with vector differentiation, fine, and we have seen the differentiation of a vector with matrix elements and so on a little bit. So probably what I will do in this class is, just to start with, I will give you some very brief questions on vector to like vector differentiation, vector to matrix differentiation, and then vector to scalar to vector differentiation. So let us distinguish them and then move on for multi-layer perceptron or multi-layer feed-forward neural network propagation in multi-layer feed-forward neural network. Okay, so let us just, for understanding, ease of understanding, I'm just decoupling between the direct application in neural networks backpropagation to the element-wise operations of or the vector calculus aspects. Okay, so even though we have discussed some of the aspects of vector calculus before, it appears that few more concepts will make our subsequent expressions writing and derivations easy. So that I will bring in now. So assume that now, so we already used some of them. We just want to summarize here, and then we want to just see that in the subsequent things, whether we are following them or whether we can directly write in such cases without going into the definitions back. Okay, so now let us assume that y equal to w into x. Okay, so let this be a function. Y is a function of x, f of x equal to y. Okay, so in this case, so dou y by dou x, if I write, what is the dimension of dou y by dou x? Can one of you tell? What will be the dimension of dou y by dou x? It will be, see, let x be d cross 1 and this be n cross 1. Okay, w is n cross d, right? So this we have seen. I'm not bringing something new. I will discuss something like on the top of this. So dou y by dou x is what dimension do you think it will be?
N cross D.
It will be n cross d, and this is equal to w. Okay, so let us see this. Dou y by dou x, say let us expand and see. So y1 up to, it depends upon how we define it. So let us see that. y1 to yn. Okay, and then w11, w1d, wn1, wnd. Okay, an element in this will be w, say let it be w whatever ji. Okay, so here yj is here, and then x1, xi, and xd. Is this clear what I have written here? Okay, so let us cross check this. So now how do we define dou y by dou x? How do we define dou y by dou x? Can one of you quickly tell? Dou y1.
Dou y1 by dou x, dou yj by dou x, dou nj by dou x.
So are you telling row or column?
Columns.
Yeah, row, if I write a column, if I write dou y1 by dou x2, See, what we have defined is previously, if f is a function of, if f is a scalar, okay, what we have defined, dou f by dou x is defined as dou f1 by, dou f by dou x1 and so on, dou f by dou x2. This is how we define. You people remember, I hope, right? Am I correct or not?
Yes, sir.
Yes.
Yes, sir.
Yeah, this is how we defined before for dou f by dou x. Now what we are trying to do is we want to stick to this definition even in this. So let the dou x1 take each component of y1 and then apply vector differentiation. Okay, with respect to x, the denominator. So dou y1 by dou x2. Okay, this is how we have actually the first column, correct? And then dou y2 by dou x1 and so on, dou y n by dou x1. Is it fine or not? Dou y n by dou xd. Is it fine?
Fine, sir.
Yeah. So dou x1. So here it all will be dou y n by dou x2. Okay, so the second row will be with respect to x2, differentiation with respect to x2. The change in x2, that is, how is that affecting in y1, y2 up to yn? Okay, similarly, change in xd, how is it affecting up to yd? So now this is what is the dimension of this now? What is the dimension of this? Yeah. You can calculate also explicitly if you want to write. So what are the elements? W11 this anyway. And this will be y2 by dou x1. What is this? W?
I2.
W?
2,
2, 1. Very good. Okay, and then what is this final dou y1 by dou
P1.
by dou x1? It is W?
P1.
1.
N1.
WC1.
C1, there is no C here, right?
N1, sir.
N1.
WN1, right. Okay, and then now what is this? W?
1D.
1D. Very good. Okay, and then this is
ND.
okay. So the overall dimension now, if you see here an element, if you write in between, it will be W Ij. Am I correct?
Right.
So it will be Wij because I am writing I here first. Here J I am writing. Okay, it is just the, so W21 is here in this case. W21 is here in this case. So it is transpose of this. Fine. So this is the dimension is D cross. Dimension is how much? D cross. Yeah. Fine. And hence this is in terms of matrix, this is equal to what?
W transpose.
W transpose. Okay. So through by our definition, dou y by dou x is a vector. See, both are vectors. Dou y by dou x is a matrix and is of dimension D cross N or W transpose directly. Fine. Is this clear or not?
Yes, sir.
Yeah, W transpose. And this is D cross N. Okay. So please note that. So dou f by dou x, if I write, it is what if x is of dimension D cross 1. Okay, dou f by dou x also will be of dimension. X is D cross 1. Imply dou f by dou x is also of dimension
D cross 1.
D cross 1. Okay. See, you should also know when you do vector differentiation, what will be the dimensions of the differentiate that you get, final result. Because dimensions are the one which is the easy guidelines for us. Okay. To easily write the answers as well in some cases. See, why we are discussing this is, when you do apply chain rule, especially in backpropagation of feed-forward neural networks or neural networks, for 1 or 2 layers, it is okay to write chain rule. If you have 3 layers, 4 layers, how many times you have to apply chain rule? every time you need to take care of all the previous things to apply again the write the chain rule and then appropriately take the whole things into account. But these vector differentiations that we see later, that these will avoid, okay, applying the chain rule, and you can decouple the derivatives at each layer. So you can easily find out layer at a given layer vector differentiation, and then you can easily relate to the previous layer, okay, without explicitly writing chain rules. Okay, and we will also see that there is a simple formula or simple rule which will connect the derivatives at a given layer. That's all. So if I have 50 layer network, if I see at the 20th layer what is the derivative, it is very simple to write by just looking at the local gradients itself. Okay, chain rule, what it requires is global gradient, overall gradient only you need to write a W. Say for example, if you have 2-layer network, to update the weights in the first layer, you need the weight update, all that. Okay, in the only to up like you have a formula and you substitute in that, and from that you compute the gradients. But whereas these vector derivatives now, we can see that these will circumvent that, and also there is a local derivative that we can write at each layer that will help us to write the global derivative easily. Okay, and there is subsequently what we discuss is the computational graph, which essentially depicts the same in a graphical structure, and which makes our job even more easy. In fact, all the deep learning softwares are built upon that computational graphs. Okay, so they have automatic gradients which are obtained from the computational graphs. So the primitive gradients whichever we have are used as a analytical gradients, and these will be used so easily to compute the back propagation. Okay, so these basic things will form a building blocks for writing the subsequent back propagation in a deep neural networks. Hope things are clear. Okay, so now here y is see, if dou f by dou x where f is 1 cross 1, then it is d cross 1. If y is n cross 1, then you are getting a matrix derivative, right? So vector by vector derivative is a matrix. You should know that. But if I take only one row of y, say that is yj of by dou x, if I compute, then it will be what? So if I take dou yj by dou x, it will be what dimension?
It will be a column matrix.
It will be d cross 1. That's all. Column matrix. Very good. Okay. So or dou y by dou xi. This will be, in our terminology, this will be, even though y is a vector, we may consider in this case as, okay, a row, but y if we really put as a vector, then we can define. We have not defined it as, okay, if it is a vector, then we can also define it as a vector, d cross 1. Okay, so this depends upon how we define. But especially when we have matrix, we don't have other go. Even if both are vectors, we need to write the perturbations or derivations, okay, of each component versus other component in a organized form or in a matrix form. So we will have a matrix. Okay, so one of them has to be made as row, even though both are vectors. We are making the we are giving preference to the denominator, and then denominator is maintaining its structure, and then numerator gradients we are writing like this. I hope this is clear.